Alright, our own project was we developed a counterweight method for measuring water loss in cotton plants. The goal of the project was to develop and design and actually construct a method of measuring water loss in the actual cotton plant. As precision ag is getting more and more popular, this will provide useful information for farmers about when and how much to irrigate the crops. Due to the heavy weight of the system, the counterweight was used to allow the utilization of a high accuracy load cell. And how lysimeters have been installed in the past, they've been actually put into the field and underground and have rows of plants and have load cells under it to measure probably 2-3 tons of soil and the amount of water loss. And what our system does, we have an 18-inch diameter by about a 30-inch height drum, and that stimulates the actual root zone of our cotton plant. And we have a counterweight on the other side that's about the same weight of our soil and our plant and our drum. And this way, the only thing we're measuring is the actual water loss that is being used by the plant and through preparation. Our objectives was to develop a system with accuracy up to 0.25 millimeters or 5%, and economic design that was under $800, and a dimension that was less than 4 feet by 3 feet in width. On the left side is our earlier design. It consisted of a square tooth frame that's like 3 inches, and on the right side of the screen is our final design. It's a triangular setup with 1.25 inch tubing. We did it this way as a triangle to cut down on material costs. And there's our final design right there.
So our weight calculation was similar to what it was during the design theory presentation. However, in that we assumed we were going to use a 55-gallon drum, and instead we bought a 30-gallon drum, and it's a little bit smaller, so our weight requirements change. Diameter is 18.75 inches, and the height is 29.5 inches, which mimics the about 3 foot needed for a root zone of cotton plant, and it weighs 16 pounds. So the weight changed to 568 pounds, but we put a safety factor on there of 30% to account for any extraneous circumstances that made the system heavier, so it actually come to 759 pounds. Last time we didn't do a structural analysis to make sure our steel would be strong enough to hold up to that heavy weight. So this time we did with the help of Kendall. We calculated yield strength, moment calculations, and shear force, and the moment and the shear force helped us calculate the section modulus, which is essentially the strength of the cross section of the tubing right there. And we made sure that our selected tubing was stronger than what was required. As you can see, the required was 0.104 inches cubed, and the selected was 0.115, so that's definitely safe. And the shear force was way less than what was required. Carbon steel is 14,400 psi, and ours was about 1,300. We did the same thing for the shaft at the pivot point to ensure that it wouldn't fail whenever we were loading up the system. And we did the exact same calculations to go through that. So we also used the section modulus to size our shaft. It came out to be 0.68, and the closest shaft size to that is a 3/4 shaft size. And once again, you can see that the shear stress on the shaft is a lot less than the shear stress of carbon steel. And then we wanted to make sure that it was going to work, even though our calculations said it would. So we loaded the entire system down with all the weights and made sure nothing was going to crack, break, or bend. Alright, I'm going to walk you through some points about our load cell. it had to be calibrated. In order to calibrate it, we used a 2-point calibration method. And basically what we did, we zeroed it out as it is now. It's balanced. And the load cell's reading that at 0 pounds. And then you can see we found some scrap metal and pieces of concrete and stuff. And we measured each one of those on a scale. We knew the exact weight of each one. I think it came out to 19.674 pounds or something like that. We wanted to get as close to 20 pounds as possible. And so our first point was at 0 pounds, second one was at 19.674 pounds. That way, the load cell will accurately read anything between those 2 points. So yeah, we put the barrel in the frame, put the counterweights on that equilibrium, and yeah, we put the weights on the counterweight side, or the steel and the concrete on the counterweight side, and that simulates water loss on the other side. So you're getting heavier on the counterweight side and getting lighter on the side of the lysimeter. We've got a few data points for you. This left column is the weight of each one of those test plates on there. And then we converted it by the weight of water for 1 cubic inch. And here, this gives you the amount of water. It says pounds here, it's supposed to be cubic inches of water. But that's the amount of water it takes to be the equivalent of the weight of those steel plates. And then these 2 columns show what the actual weight of the steel plates were from the scale we measured. And the other one shows what the load cell actually measured. They're really similar numbers. Go to the next slide. This shows you the accuracy of what the load cell is reading when you have a given weight. 0 pounds is reading 0.039 pounds, so a little bit off, but it's still pretty accurate. This is a calculator we came up with in Excel. Actually, Kendall helped me out, and we used the slope and the intercepts of the 2 data points. Right here, we used the slope and intercepts of those, plotted it as a y is mx plus b, and y would be the actual weight, and our x is the load cells reading. That way we can plug in any number we want to and see what it would read. This graph shows the solid black line is where the load cell should be measuring, and then the points along that line are what it actually measures, so you can see it's very accurate.
As you can see, a little change in weight really changes what the load cell is reading. So we wanted to make sure our system wasn't like collecting moisture and changing the weight of our cinder blocks. So we did a test on our cinder blocks to see how much moisture can get absorbed by the concrete, and how well we painted our cinder blocks with some stuff that will, I guess, that's waterproof, and it's just a mixture of
so yeah, it's a synthetic coating that you mix with paint, and my friend's company makes it, and we tried to use it. We want to test and see how it worked.
So we ran a little test. We have the control without the painted solution on it, and then we have our blocks with the painted solution. And as you can see, it's about a pound difference once we soak the cinder blocks. So us painting on the synthetic paint sealant, I believe it's going to be a good thing and make our readings more accurate. This is kind of just a breakdown of our costs. In the end, we spent about $815, and I guess labor was one thing, you know, we weren't real sure about, but I guess we ended up having a few leftover pieces of metal. We had one leftover stick of the square tubing and a little bit of the angle iron, so that's going to allow Amanda Hyatt over here, she's going to go down to Blackville and be making a lot of these, so that can help her out with some of the material costs. And a few problems that we ran into. since we calibrated the load cell with those little test plates, we're really only as accurate as the scale that we use to weigh those with, which is just like a little scale that we use in chemistry lab. And also, before we hook up the load cell, we have to get the whole thing balanced. And it's kind of hard to tell if you're perfectly balanced or not. Of course, if one side's heavier than the other, you can obviously see it flip over to the other side. But we can kind of use a level, or what we'll do is when we get it close to where we think it's balanced, we'll hook it up to the computer and see what kind of voltage our load cell's reading. And if it's reading like 30 volts, we just move some of the blocks in or out to get it to go to 0. And then also, we can't really help external forces like temperature and wind, but if our system's bouncing up and down for some reason, it puts the funky reading on the load cell. And also, we're not really sure how moisture could maybe affect the metal. It might, we've got hollow tubing, so it might somehow get moist in there and affect it. So some recommendations: we could always get a more accurate load cell, get a more accurate scale to calibrate our test plates with. We could do some more calculations just to make sure that our strength and everything's all right, and just make sure that no water is being soaked in by the system. So some outcome, get more accurate water readings for plants, and we can use, we're doing it, Dr. Piero down at Blackpool wanted us to do it for cotton plants, but you'll be able to do it for any kinds of plants, and you'll be able to do it for different soil types, see how the drainage and evapotranspiration is affecting that soil. So in the end, we measured up to an accuracy of 0.017 millimeters of water, or millimeters off, and we wanted it to be accurate to 0.25 milliliters of water. And we're going to try to keep it under $800, but we're at $815, and that could just be because of labor costs. And then we're about at, we're just under the sizing requirement.
What we're going to do now is we're going to actually show you how we calibrated this. Because if you move any part of the system and you have to recalibrate, it's a pain in the butt. I think Tom and Taylor are going to show you how we do that.
Alright, one thing you got to know is our load cell has an overload rating of like 100 kilograms, so that's about 200 to 220 pounds. So you got to make sure that you don't put too much force on the load cell, or it'll, I guess not.
What's the weight that you got on it in that bucket right there?
The bucket itself, I think, is
bucket, soil, water, just ballpark. Just to put it in perspective for people.
568.
500-600 pounds, but you can only put 200 pounds on the load cell. So
yeah.
That's the importance of that counterbalance.
Yeah, that's why we had to have the counterbalance. So we have it where you can disconnect the load cell right here, so you can make sure that you're not putting too much weight on this side. So what we do is we first load up this side with our cinder blocks, and we've previously done calculations on kind of where we want to put this plate. And then once we get the center blocks on, we're able to move our lysimeter onto the system. And then we kind of look and see if it looks pretty balanced. And you can kind of feel it and see how much weight you need on one side or the other. But once we get that down pretty close with feeling it and with your eye, we connect it to the load cell. And the load cell's not calibrated at this point, but it's able to read voltage. And so we move this around to try to get the voltage reading to 0. And then that's about as balanced as we can get it. So then we have like the naked system. We calibrate that to 0. And then we add about 20 pounds onto one side, and that's going to represent water that's going to be lost roughly throughout the whole growing season, I guess. And as we take off weight, we'll be able to see just how accurate our system is.
So for example, right now, there's a program we downloaded from fidgets.com, which is the person who makes our load cell, and it is it has inputs and whatnot, and it reads that as a voltage, and then it converts that into a converted value, which is what it's reading in pounds per se. So right now, in the first input we put 0 pounds because we're at equilibrium, and you put the total weight of our known weights right here, these test points, and that's what, 19 pounds or so. So what we do, you ready?
Yeah, we've got it set to 0 right now. The bridge value, which is what you're measuring the voltage, is it's 0.34 volts. We're going to set it to 0 with the weight on there. Taking it off is going to simulate adding water, but you can do it either way.
Yeah, the load cell can read like a
Positive and a negative for gaining a
So I just took off this weight right here, and that's 3.238 pounds. On the same time? Calibrated?
Yeah, what we're going to do is we're going to take all these weights off to get it zeroed.
Basically, that other side is gaining 19.674 pounds by taking off from this side. Now we're going to set the 0.2. If you add weight to it, right now the load cell is reading that they're 19.767. It's kind of fluctuating back and forth. If you add weight, it should subtract it. So that weight is 0.944 pounds, and now it's reading 18.5, 18.63, fluctuating back and forth. So simulated losing water.
Any questions?